My name is Trung Nguyen, and on behalf of our team, I will present some preliminary results of our current study on high-resolution mapping of carbon debts from harvesting beetle-killed lodgepole pine. The recent changes in climate allowed an eruptive mountain pine beetle outbreak that killed millions of acres in western US since the late 1990s. This video shows the expansion of mountain pine beetle-induced mortality in Colorado, Wyoming, Idaho, and Montana from 2000 to 2012. As of 2012, mountain pine beetle impacted nearly 3.4 million acres in Colorado. While this is really sad, it does provide an opportunity for bioenergy production because this beetle-kill feedstock requires no cultivation and may also have a highly favorable carbon balance compared to other forestry feedstocks. In that context, the USDA funded the Bioenergy Alliance Network of the Rockies, Banner, to figure out the most sustainable use of beetle-killed as a bioenergy feedstock in the region. Banner approaches the issue in a very holistic way with various task groups from feedstock supply, logistics and processing, system performance and sustainability to education and other extensions. Within the System Performance and Sustainability group, we are tasked with quantifying the ecological impacts of beetle-kill harvest, the financial viability of the supply chain, and potential for life cycle greenhouse gas mitigation. One of the important questions that we ask is, harvest or not harvest? And if we harvest, what are the carbon impacts? To answer such a question, we conducted a case study on a subset of a larger Banner region. This area consists of lodgepole stands in northern Colorado and southern Wyoming, with an area of around 509,000 hectares and an estimate of 71 million metric tons of lodgepole biomass. The landscape is represented by a raster of 30 by 30 meter pixels. The objective of this study is to investigate the carbon debts due to salvage logging and whether the harvested stands can repay those carbon debts on their own. If so, how long would it take? For this study, we built different predictive models using the available observed data and applied these models with different spatial input layers to predict the carbon debt and payback time for the landscape. Here is a quick overview of our method. First, we acquired measured data and ran them with the Forest Vegetation Simulator, the FVS model, to create a dataset for model training. We then built surrogate models of the FVS to predict carbon debt and payback time and ran those surrogates with the spatial input layers to produce the maps of carbon debts and payback time. We acquired data from 438 lodgepole dominant FIA plots in Colorado and Wyoming, measured from 2002 to 2017. Lodgepole dominance was defined as 65% of lodgepole species composition. These stands have an average basal area of about 30 meters squared per hectare, tree count of about 2,000 trees per hectare, and an average stand mortality of 15%. Before simulating these stands with FVS, we evaluated the default FVS growth models and found that the FVS tended to overpredict the growth of the main species found in our observed data, including lodgepole pine, Engelmann spruce, subalpine fir, and aspen. Therefore, we had to calibrate the model before carrying out the simulation. For this, we constructed different chronosequences of FIA data and used the means of those sequences as benchmark to calibrate the FVS model. We calibrated each species separately and then readjusted them in the mixed lodgepole stand. This graph illustrates the chronosequence used to calibrate the final mixed lodgepole stand. No harvest and harvest scenarios were simulated with the calibrated FVS model. We calculated the carbon debt at time t as the difference between the total stand carbon of the harvested stand and the no harvest stand at time t. The carbon debt is reported with negative values in this presentation. The payback time was calculated by intersecting the carbon debt curve with the y=0 line. We assume a linear interpolation between the last negative carbon debt and the first positive carbon debt value. There is no payback if these two lines do not intersect. We use random forest machine learning algorithm to create FVS surrogate models to predict carbon debt and payback time. 6 input features including years after harvest, aspect, slope, elevation, dead biomass, and total above-ground biomass were used to predict the FBS modeled carbon debts. The carbon debts were then used as an input to predict the payback time. We applied the carbon debt surrogate to our spatial input layers to create the maps of carbon debt over time, and then used these raster to predict and map the payback time. Here are the spatial input layers that we used. Slope, aspect, and elevation layers were created from the topography data. The above ground and dead biomass layers were created from the FIA and all the spatial data. They are the products of a different banner team. Here are some of the preliminary results. I'll present the outcome of the model calibration, some highlight in the input and output relationships, and the results of surrogate model building and the mapping of carbon debts. This graph shows the FBS model calibration based on the total stand carbon. The total stand carbon is on the y-axis and the stand age is on the x-axis. The blue line is the default FBS model prediction. The black line is the mean FIA chronosequence, and the red line is the calibrated FBS model. We only calibrated the model based on the 40 to 150 age group of the FIA chronosequences because we were not confident in the early aged and older aged plot data because of either low numbers of plots or some funky behavior in the data. Different output metrics were calibrated at the same time to make sure that the model behaves reasonably. These include total stand carbon, live basal area, dead basal area, tree per hectare, quadratic mean diameter. The takeaway here is that we were able to improve the FBS model fit to provide reasonable estimates of forest successional dynamics. Here are the carbon debts over time for the FIA plots. We found that of the total 438 plots, 150 had a payback time and 288 had no payback time over a 200-year simulation. Minimum payback time was around 4 years and maximum was almost 200 years. The initial carbon debt ranged from 0 to 130 megagram of carbon per hectare. Carbon debt tended to increase a little bit in the first 10 to 20 years after the clear cut and decreased as the harvested stands developed over time. A quick exploration of the data revealed that years after harvest, initial above ground biomass and the initial dead biomass, the upper plots, tend to have higher influence on the carbon debt than topographical factors such as slope, elevation, and aspect. This box plot shows the psi index over the payback of carbon debts. It reveals that the stands that paid back the carbon debts are the ones that had lower psi indices, meaning less productive sites. This brings up a pretty interesting trade-off between the economics of stand harvest and ecological impacts. Because on the economics perspective, higher productivity sites tend to be preferred, while this result shows that one is better off in terms of carbon debt and payback time by harvesting lower productivity sites. Here is the result of random forest model training. The surrogate model of carbon debt exhibited high accuracy with the RMSE of 5.6 megagram of carbon per hectare and the R-square of 0.97. The variable importance analysis shows an expected ranking of variable importance in explaining the variation in carbon debt outcome. The Spearman's rank correlation coefficient on the left shows how each variable correlates with carbon debt. Except for years after harvest, increases in other inputs resulted in increases in carbon debt. This slide shows the landscape average carbon debt over time. First, this shows that the landscape won't be able to recover the carbon debt by itself within the first 100 years after harvest because the average carbon debts are always below zero. Second, the most dynamic changes in carbon debt on the landscape happen within the first 60 years after harvest. The carbon debt seems to level off after 60 years, indicating there is a carbon deficit of around 30 megagram of carbon per hectare from the feedstock production that will need to be offset by other means, such as biochar addition as a byproduct or CO2 offset from production and use of wood-based biofuels. Here are some maps showing the spatial distribution and changes in carbon debt right after harvest and 50 years and 100 years after harvest. The color range shows a carbon gain in blue ranging from 0 light blue to a maximum of 8.3 megagram of carbon per hectare dark blue. Carbon dash are shown from light blue to yellow, representing 31 megagram of carbon per hectare, and to red, representing a maximum of 124 megagram per hectare. The maps show a drastic change from year 0 to year 50, and a slight change from year 50 to year 100. Also, we certainly can see the spatial heterogeneity of carbon dash throughout the landscape. This indicates the need of further optimization on feedstock harvest and facility siting to minimize the ecological impacts of salvage logging. Those are the preliminary results. In the future, we will extend the analysis to create the maps of payback time for the study region. We're also planning to compare the effect of different harvest methods on carbon dash and payback time of the landscape. The results of this study can serve as an input for further analysis to optimize the feedstock production for biofuel with a broader scope and system boundary, such as by considering life cycle and supply chain of a biofuel product. And finally, I just want to acknowledge the funding source of this study. And with that, I will end my presentation here. Thank you very much for listening, and I'm happy to take any questions that you might have.